Why do people explore? That's a really profoundly interesting question. We've looked at the sky for as long as we've been alive, and we've dreamed in stories and in movies of traveling to the stars. Why? We want to see what's out there. The problem is that while we can go to the moon and while we actually have within our power to go to Mars, we don't have a well-defined way to get out of the stars. So what we're proposing is precisely that, a well-defined and logical way to go to the stars, not with humans, but with robotic probes. So I'm a professor in the physics department at the University of California at Santa Barbara. This department is one of the top 10 departments in the country in physics. We have a group in our department, the Experimental Cosmology Group, that we started in 1987, and it's a very dynamic group. Some of those students are also focused on applications of directed energy systems.
The main mission behind the Experimental Cosmology Group is to advance science and advance directed energy studies and its applications.
There's an aircraft flying overhead that you hear. That aircraft can only fly about the speed of sound, but that's way too slow to explore the stars. If you were to maintain that same speed and wanted to go to the nearest star, it would take you more than 5 million years in that aircraft. In our system, with the smallest probes, it could take as little as 20 years.
If we want to get to Alpha Centauri in 20 years, we have to take our ideas and scale them down. And in order to do that, we've set up a vacuum chamber to simulate space conditions.
Directed energy system is basically like a laser pointer. You take a laser or a flashlight, you turn it on, you direct energy. That beam can be used for many purposes. When it's taken to extremes, it can be used to deflect an asteroid coming into the Earth. It can be used to propel a spacecraft.
In order to get to the future, we need to take small steps. I like to think baby steps, right? Some of those include just laboratory measurements of the thrust that you can get from ablating an asteroid, the thrust you get from propelling a spacecraft.
If you scale that up to large-scale directed energy systems like we're proposing, that force becomes significant.
Theoretically, the wafer spacecraft is actually 4 inches by 4 inches, almost as thin as your hair. And these probes would literally be a spacecraft on a chip.
The propulsion system is the laser which stays at the ether on the moon or nearby. You fire it and then it's gone. If we reduce the spacecraft to a wafer, which would have things like imaging sensors, cameras for looking at the stars for orientation, and then a laser communication system to communicate back to the Earth. But keep in mind, the same system, this is a very important point, the same system is used not just to send out one probe, but to send out an armada of probes. It takes about 10 minutes to accelerate up a wafer to 30% the speed of light, and that's it. You could send 100 per day or more. You could send nearly 40,000 per year.
Once we have thousands of spacecrafts out in space, we can look at many things out in space that we've never been able to explore before, such as the solar gravity lens, Alpha Centauri, the closest star.
When we really begin to look at the issues of sending humanity into interstellar travel, it becomes very different than the movies. We're not really the ideal creatures to be traveling. Really what we want is not necessarily to spread our bodies throughout the universe, but to spread the capability of replicating ourselves, or our spirit, our inquiry, our biological subsystems.
Obviously, you're going to start out with critics and people that are going to question you. But then, as we can actually see people like starting to like our idea more and more and like coming to it. And I think that's really special, and that's where the optimism comes from.